Good evening and welcome back to Vegas October 1 Sounds. Tonight we're going to do a cursory view on some of the graphs that I use to analyze the data from the initial phase back, I don't know, a year and a half ago, close to 2 years now, in looking at this data that I developed for the October 1 incident. There are literally hundreds of graphs or types of graphs that I look at almost on a daily basis, but there are some graphs that are more frequently used than others, and I'm going to show you some of them. Now this excludes all spectrograms and all that stuff. This is mainly just regular old everyday plain Jane graphs, and I'm going to try to bring the level of understanding of these graphs up a little bit so that you can see what might be possible in this analysis of the data. And I'm also going to try to pique your curiosity, because if there's something that you want to look at that I haven't thought of, feel free to make a request of me, because it's not a year-long process to modify the program that I've developed to include your type of request. In fact, a lot of times most plots end up being just a few hours work to incorporate in, and if it's something that I haven't thought of that is very useful, I welcome it. In fact, I'm an engineer, of course, as I've explained many times, and my way of thinking is completely different from the average Joe. I think in terms of waves and frequencies and timing and probabilities and convergence and all these things that are unique to my profession. And so all the data I collect and all the questions I ask of that data are couched in those terms. And it's a very narrow mindset. Now, I don't want people coming along and asking me, okay, can you show me, where the shooter's located, because that's asked 1,000 times. It's been answered by various people already, including myself in my lag plots. I'm looking more like for the things that I haven't asked, that other people haven't asked, that once I expose you to this data and just a few of the simple graphs that I have available, that it might open your mind a little bit and say, well, wow, I didn't know we could do that. And if we can do that, why can't we answer this question, and here's how we go about it. So if you've got a request, propose something. Okay, Richard, I'd like a plot that shows me the price of tea in China over time, with it displayed as a scatter plot or a linear plot or a contour plot. And if you're unfamiliar with these types of things, you can go to the web page for matplotlib. All you have to do is type in Python space matplotlib, and then go look at the example. Well, here, why don't we just do it? Go up to here, and we'll type in DuckDuckGo. Yeah, of course. And it'll bring you right up to matplotlib over here or anywhere. And then from this page you can see, an introduction to what this program is. But the examples is the curious part, is the interesting part, because under the examples it's a gallery of all the different types of plots that are available in this library. And this is the library that I use. So if you can determine what goes on the X and Y and Z axes and the flavor of style, how you want it presented, we can do it. But there has to be a real question behind it. You can come along and say, I need to have this, because if I have this, I can answer this question, and I think this question is important. That's a very valid request, and if you can think of it and it's important to you, it probably is important to me, and I may not have asked it because of my mindset. Okay. Similarly, there's another library that I use. called Librosa, and you type it in and up will pop Librosa 0.70 documentation. And you can go here. This is a little bit more technical, but anything that's contained in this library I can incorporate into my program in fairly short order. And this library is all about signal processing for music and audio analysis. And these are the routines that I use when Sonic Visualizer doesn't get the job done. And you've seen some of them. You've seen the results of some of them. Okay? So, for example, let's pick one here. Let's go to spectrogram decomposition. Okay? There are 3 routines that it offers, and if you click on, let's go for example HPSS, which I know to be harmonic percussive source separation. Okay, and it'll tell you what it means. It'll give you reference to some papers. It doesn't give you the links, but you can type these in, and then it'll give examples of how to use it and what the output might look like. This is one that I use. This is the exact same routine. Of course, they're all parameterized that I used on the 3-round discharge inside of room 135 to separate out the echoing from the real source of the shots, and so that we could count them. And anything that's possible in here, if there's something that you'd like to have done or attempted on the signal, we can do it. So this is a wide open box, and sometimes these are a little bit more complex to do. They might take me a week in my time, which is roughly 2 hours a day, or a week would give me about 10 hours. I can only in 10 hours get pretty much anything done prototyping that I come across. All right, so that's the scope in which you can ask to be done. The data that you can ask to be done is strictly muzzle blasts. That's all I've got now, 7,000 points or more, and expanding daily of muzzle blasts. Soon I'll be incorporating sonic shockwave, or the shock waves, and then after that I'll be incorporating, hit sounds. So we'll be able to ask all sorts of questions about all sorts of things. So at the moment, determining lag is a whole separate routine that's being developed, and it's pretty primitive in its form. So stick to muzzle blasts, and if it's a question about that, we can get it done. All right, with that said, let's go to, this is my development environment here with Python, and talk about a couple types of graphs. After we've marked these things in Sonic Visualizer, that is, we mark every muzzle blast in on the spectrogram or wave plot or whatever, and then we export that data to a table, a text table that my program can read. I can then plot it or massage it into anything I want. And tonight I'm going to be presenting 3 different sources of information. One is from a machine gun, an M240 series, magazine fed, and one is volley 7 from Oasis Apartments, and the other is volley 10. And these kind of represent the extremes of the different rates of fire, shall we say, with volley 10 being the worst, volley 7 being pretty good, and then the machine guns being completely different, the M240 anyway, completely different and more consistent than either of the other two. So when we take that raw data and we plot it on a time on the x-axis, then what we can see is this little graph of where each muzzle wave occurred, which for this machine gun, you can see that they all look very, 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 very regular. So if I were to listen to the audio associated with this machine gun, they all sound like they were coming out at nice, neat intervals. And overall, I call that the cadence. And the cadence, I would say, would be very regular. Now, if we take and look at the cadence for volley 10, you can see immediately where there's short and long and everything in between. And particularly towards the tail end here, people claimed that it sounded like it was dying out. It was. Okay, 1 second. Yeah, so we're recording. I just want to make sure I was recording. Anyway, so we did the machine gun volley 10 and then volley 7. Volley 7 looks a whole lot more consistent in its cadence than volley 10, with the exception of the up front here. Okay, no, so that's one way of looking at stuff. I rarely look at that unless I want to compare the same volley across multiple videos, and then I'll take, in this case it would be volley 7, and I'd stack the next video down below and then the next one down below, and these lines had better line up, because after all, if both the shooter and the recorder are fixed in location, then there should be no difference in the timing except for when it initially arrives. So if we put the first shots together, then they should all line up. And if they don't, that means that either the data is bad or one or the other is moving. So the very fact that we can take volley 7 from multiple videos and line it up and there's no difference in timing means that both the recorder and the shooter were static, or they were both moving exactly parallel at the same time, which isn't the case. Alright, now I'll repeat that. The fact that I can line up volley 7 across multiple videos and their time at which the muzzle waves occur relative to the start of the volley is identical means that both the shooter and the recorder were static. So if your theory, your favorite theory, proposes that the shooter was flying through the air in a helicopter, I'm sorry, but you're out of luck. It just can't happen. If that helicopter was moving relative to the recording way in a substantial way, then it would be recorded in these little deviations here. All right. So that's one very good use of that plot. Now, if we take that data and we were to, let's go to a different one here first. Not there. Oh, if I were to put all those together, it makes no sense here whatsoever, because they're different volleys, so it just fills in the gaps. Anyway, if we were to take and measure the time between each of these rounds, and we call that delta, and plot it over time or relative to the round number, such as here, which is this is a plot of the time between the round versus time for the M240 of N3, which is one volley consisting of 49 rounds. Here we see that over time it started high and went low. That is, the gap between bullets got smaller the longer the volley went on. Now this volley went on for about 0.4 seconds. So how much did it decrease? It went from a high of 0.086 to a low of 0.072, let's say. Not too much at all. And now if we did the same thing for Oasis Apartments Volley 10, then we'll see it went from a low of somewhere near 0.075 to a high of 0.225, or 3 times, or 10 times what the machine gun did. Okay? So just because it looks jagged, it's not really too jagged, but the scale over here goes, is, let's say 0.0. Yeah, the scale is 10 times zoomed in compared to this one. So let's see, I find all those, so let's see if I can find those all plotted on the same graph so that you get a real good idea of what's happening here. Now, did I plot those at the top? Yeah, I should have plotted those at the top. There we go, right there. So here I plotted delta T versus, well, that's shot number. I want time. Oh, maybe I didn't. I'm sure I did. Yeah, we can do it on this one anyway. In this case, rather than plotting it versus time, I plotted it versus shot number, which is approximately the same, but a little bit more useful. So here we can see the machine gun, where the time between shots indicated by the variation in the line, compared to either volley 10 or volley 7, is relatively small. Okay, so those other scales, which looked large, when put onto the same scale here, all comes into perspective. Volley 10 being the green line here varies substantially more than volley 7 if you exclude the first few shots. So in this graph we would say that the most consistent sounding is the machine gun, the next one is volley 7, and then the worst is volley 10. Alright. So let's go. So if we, instead of measuring the time between shots, if we plotted the RPMs, which is a straight derivative of the time between shots, because the instantaneous time between shots, if it's 0.1 seconds, if you take the inverse, which would be 10, and multiply by 60, you'll get 600 RPM. So the time, delta is directly related through a simple formula to RPM. So if we convert it to an RPM plot, and we plot them all on the same one, this green, or this blue one over here is the 240, and you can see that it varies by just about 100, from 700 to 800. Volley 7, the orange, has a low of 300 and a high of little over 700, or a spread of 400. But only for the first few, and then the rest of them have about 150 RPM variation. Volley 10, on the other hand, for the entire volley, goes crazy all the time. It goes from over 850 to a low way down here of 250. So that's a 600 RPM difference over the length of that volley, and if you were to take the average, it'd probably be somewhere from, let's say 750 on the high to 600 on the low. Yeah. So quite a bit of difference there. So that gives you a quick indication there. That's all plotted on one graph, which is what all these plots are. Here we do a stem plot, which I'll come back to. We just covered that one. All right. In this data run, what I did was I plotted 7 or 8 different types of graphs individually, so I'd get a graph for each volley, and then I'd take that same graph and plot them all together on one graph, so you get a comparison between. Some of them don't make a lot of sense. Some of them need some modification and help so that they're more distinct. It's a work in progress all the time. So anyway, this is a histogram plot with all 3 volleys on the same graph. The blue is the machine gun, the orange is volley 7, and the green is volley 10. What we see is that the machine gun has a very well-defined and narrow center. It's symmetrical about that center, and it occurs right around, I don't know, let's say 0.080, with very little variation. That is delta T. So what we can say is that for the machine gun, there's substantially less variation in delta T, because this is narrower than there is for either of the other volleys, as you can see, because they're much wider. So in terms of total variation from shot to shot, on average, volley 10's the worst, volley 7's in between, and the machine guns are substantially different and more well defined. The fact that if you draw a line right down the middle of that histogram for the machine guns, and that there's equal number of shots on both sides and they take a very symmetrical form, is typically what you would expect of a natural process, because it forms what we call the normal curve, and the normal curve is occurs all throughout every process, practically every natural process. If you take a bunch of IQ measurements and you plot it, you'll end up with a normal curve. If you take the variation in small variation in part size for a bunch of parts, it'll it'll form a normal curve. So I would expect that any well-tuned machine gun that's doing its business is going to form a normal curve, and that normal curve will probably be dominated by the variations in load or the variation in spring discharge or gas tube or whatever is causing it. Which then comes to our volleys, and since they're all over the place and they aren't forming that normal curve, you have to expect that there's something else going on. So essentially a histogram says that if you look at all the times between the rounds for volley 7, the majority of them are going to land right here, but then there's also these other peaks over here. And when there's more than one peak, we call that in this case, if there's two, a bimodality. There's 2 points of where the gun's preferring to come to rest in terms of its frequency of the RPMs or the time between the rounds. And that's what volley 7 shows. With the volley 10, there's multiple. There's one here, there's one, sort of a group in there, and then again out here. So it's a trimodality operating mode. And that's very, very interesting. Okay, so that means there's, in these cases, up here there's at least 2 or 3 forces driving volley 7, and in volley 10 there's 3 or 4 forces driving it. Now it could be that, volley 7 has 4 forces also, but one of them was under such control that it becomes irrelevant. But they're all relevant in volley 4. And that's what a histogram can tell you. It can tell you approximately where the preferred values are. In this case it would be delta T. If we invert it, it would be RPM. And what their spread across time or measurement is. If time is the measurement, then that's what it's spread. If inches were the measurement, it would be what their preferred measurement in inches would be. So a histogram can be very, very useful. It's kind of a cheap way of of estimating what the spectrogram might do, except that it's not over time, it's over count. Over here you can see the count is. So for example, in volley 7 near 0.080, we have, just in one of those columns, we have 100. That can't be right. There must be a mistake there in terms of the numbers on the size, because it can't be more than 100 in there, because there aren't. So I mislabeled that. But anyway, the distribution is correct here. There may only be like 10 or something there. I think that's what I had, was off by a factor of 10. I'll go back and look at that. Anyway, so we could, when this scale was correct, we could just take this line over here. Let's say it's 5. So in this case, on these numbers right here at 0.0, I don't know what it is, 79, you'd have 5, and here you'd have 10, and back down to 2 or 3. Okay, histogram. We can look at the histograms individually to get a better idea of what's happening, because the scale automatically adjusts to the maximum. So in this case, where above the whole thing was narrowed down to one block, this one is pretty wide, but you'll see that the values for 0.086 to 0.074 is a really small range when compared to what's happening here, which goes from 0.075 out to 225. But because the max and the minimum were small, it appears to be wider spread out. But this is the histogram for the machine gun, and again you can see that if you draw a line right down the middle, it's evenly distributed sort of on both sides, and that if you were to scrunch it together in a small time scale, it's just one preferred peak. That's what we call peak. Whereas this histogram for volley 10, not only is it not symmetrical about the line in the middle, but it has this point up here that's a preferred and dominant peak, and here's another peak. These probably aren't so much. Those are outliers over there. And so what we can say is that, again, it's a bimodal preferred mode of operating mode. And we can also say, because it's not symmetrical, that the left side of this is more preferred than the right, because after all, on the left side there and on the left side here, there's measurements, but then the minute you hit the peak, it rapidly drops off. So that's very indicative of some process going on in there, or some finer structure of the variance in the rounds between, or the time between rounds. So volley 10 should provide some interesting analysis. Volley 7, on the other hand, not so much, because if we draw a line right here down the middle of that one, it's kind of equal on both sides, and over here, that may or may not be, it might be a bimodal operation, but if you viewed it as one entire group, since it has a very substantial base down there, and you drew the line right around here, it wouldn't be a Gaussian or normal distribution because of the lack of counts in the middle, but it would still be roughly the same, with a peak right here around, I don't know, I'd have to divide that up, less than 0.1, greater than 0.08. Alright, so we've covered histograms, we've covered just straight, where was it, those, or events over time. We've covered a little bit about RPM, both an RPM, and but let's go back to the RPM for a minute. Here's an RPM for volley 10. What do we see? Well, first off, we see it's all over the place, right? But we also see patterns in here. I mean, let's take the time from here to there, and there's probably about, let's see, that was meant from that's about 3 seconds there. For those first 3 seconds, we have two groupings, and they both look similar to one another. They both go up to this peak very quickly, and then they come down. Go up to the peak, come down, and they both have a little bump in the middle. Okay, one's wider than the other, but they're similar. Okay, so that's a phenomena that has some forces driving it, causing them to be similar. Why are they similar? If we were to look on a larger picture and say that, well, it's cycles. It cycles from, this is a cycle, that's a cycle, that's a cycle, that's a cycle, that's a cycle. So that's one pattern we need to address. This is another pattern. And then these patterns over here, which go up and down pretty quick, also need to be addressed. And there seems to be something happening at the top of the peaks, where right near the top of the peaks, there's a little grouping of 4 or 5 in each case, and then immediately after it drops down quickly with a couple, 3 or 4 shots too. Over here, this might be the same phenomena there, but it takes more shots to get all the way to the bottom. For example, this one over here goes 1, 2, 3, 4, 5, 6 from top to bottom. Over here, this one takes 1, 2, 3, 4, 5, 6, 7, 8, 9, or 9. This one takes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This one takes 1, 2, 3, 4, 5, 6. So you see there's some similarity here. These, when they oscillate on this side of that 3-second mark, take about 6 to go from the top to the bottom. And there's a grouping at the top of 4. There's this very regular pattern. Okay, and then this one, which kind of was the start of it all. So this little divot, and that little divot are all some minor variations on this thing up here where it didn't divot, it went up. So there's some real patterns there. And we can look at this finer structure from these types of graphs and say, yeah, we might be able to decipher over the long haul, by looking at enough volleys or looking at it carefully enough, what the forces are that drove it to this pattern. Be it muscle fatigue, failure in the weapon itself, a straight function of not applying enough force to the bump stock, or several different other variables. Okay? And then we can also notice that the entire thing, if you draw a line right around 625 RPM, it divides this thing into two halves that have the same number of shots on the upper side versus the lower side. That's also interesting. That same analysis for 7 is completely different. Okay, 7 doesn't have these major cycles like that. It has this sum cycle, but it's sort of like a smoothly changing thing there, and with the exception of these first shots, which are just out of control. But along this smoothing changing, the variation is very small, and I don't see right off the top of my head any pattern except that it goes up and then it goes down, it goes up and then it goes down, it goes up and then it goes down. So that indicates a coupling. That is, one shot to the next, there's a dependency. But up here in volley 10, it doesn't always, I mean, they go up, 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 up. These don't. They go up, then down, up, then down, up, then down, up, then down. Why is that? If they're the same type of weapon with the same mechanism, what causes them to be different? I mean, if I had two AR-15s, whether it was Colt and some other manufacturer with the same type of bump stock on them, and it's one person operating it, what caused that? Or is this the signature of another person? I don't know the answer, and I'm going to have to do a lot more data collection outside of Vegas to see. I'll go out and I'll collect 10 different people all shooting bump fire, and I'll get for each person 5 or 10 different volleys on a couple different occasions, and I'll put that into these same types of graphs, and then I can look at what the patterns are, and then I can draw some conclusions. But I can't just do that by saying, oh yeah, I looked at this graph and that's multiple shooters. That's a bull crocky to make that leap of faith, which is, by the way, what most of the researchers in Vegas do. Now, there are some good researchers, but most of them find one little speck in the sky and say, see, there's an attack helicopter. Oh, come on, give me a break. It takes lots and lots of data to first make some observation and propose the theory and hypothesis, and then go out and find all the other data to establish a baseline that under conditions different than Vegas, to prove that there is in fact a phenomena and that was the cause. Okay, so and let's see, we should have one for the machine gun. What does the machine gun do? Well, if we draw these lines right down through the middle of it, and we could normalize it and make it a flat curve, but what happens? Well, we got 2 up, 3 down, goes up, down, couple, 2, 3 up. So basically it's kind of like volley 7. It's up and down, with maybe 2 up and then 2 down. 2 up, 1 down. Yeah. Let's see. Pick a flat. So we go up, down, 2, 2, 2, 4. So in this case, rather than being 1 up and down, it looks like it's a 2 up, 2 down with small variations. So again, this shows some dependency from one round to the next, which I kind of expected. I mean, in a gas discharge system, if there's variations in the load, then which means there'll be consequently variations in the chamber of the muzzle, which is where the gases go through the muzzle, and then it goes through this orifice that goes into the gas tube, and then the gas tube powers the recycling it to the next bullet, the eject and whatnot. Then if one round has lower pressure, then it's potentially going to cause the gas discharge mechanism to operate more slowly. That's a hypothesis. I don't know for sure. I'd have to go research it. But it's possibly one explanation. There could be changes in the weights of the bullets or anything there. Alright, where does that leave us? Okay, this is a delta t over time. Now, instead of RPM, we could, we plot these things with delta t's over time, and it's, as I explained, it's just 1 over the RPM divided by 60, or inversely, 1 over the delta t times 60 gets you the RPM. And in this case, these patterns might be more visible, they might be less visible. Both plots are available, and each has their purpose. Alright. And now we come to what I call a stem plot. And let's not start with the machine gun. Let's start with volley 10. Here we have volley 10, and the red line represents the mean of all the times between bullets. And in this case, we see that the first one was way off. But after that, we go into these little patterns. There's a pattern. Here's a pattern. Here's a little bit different pattern, but kind of similar to that. And then we get these patterns. Whoop, whoop. You see, most of them are down below, and it goes up, down, below, up a little bit, down, below, up a little bit, mostly below, then up. See these nice little patterns. That's indicative of some process going on in there that we need to understand. And is ripe fruit for the picking. You just have to have the diligence to get enough measurements, make some observations, propose a theory, find other cases that support it, and come to your conclusion. Doesn't mean it's entirely correct, because your data sampling may not have a large enough scope to identify all of the parameters, but you have something rather than just hypothetical. Here's volley 7. You see that it doesn't have the same pattern as volley 10 at all. In fact, the fine structure here just pretty much looks like, well, in this case it's predominantly under, in this case it's predominantly above, and here it kind of splits it. So there might be 3 different modes of operation there, but they're all pretty close to the mean except for the first few shots. Alright, and of course the machine gun, flat. But in this case we got slightly different plot. We got delta T versus shot count. Delta T versus shot count is really good when you want to compare one volley to the next, or compare the same volley over multiple videos, because that way all the shots occur at the exact same time. It's just the height indicates the difference in the timing. And I should have plotted one out here so that we could see it in another video. I'll cover that in another video. Let's go back to the top and make sure I got the regular graphs. Yep. Okay. Now we get into the little bit more esoteric. After we've done the standard, over time, over shot count, delta T, RPM, and the histograms for all those things, then we come into a little bit more esoteric ones. In this case, what it is a magnitude spectrum. And what this graph measures approximately is, it tells you how regular the changes in whatever you're plotting, which in this case is events. So we plot the direct time from the events relative to the start of the video, and we're basically going to say, okay, for this frequency to that frequency, which I haven't indicated on this scale, what's the probability of that frequency occurring? So whatever frequency this represents over here, this is the highest probability of it occurring, and then as the frequency goes up, the probability goes down. And as you can see, all three, or this gun and those 2 volleys, all have a very similar curve. The machine gun, of course, being the most smooth, and then whatever these are, let's just call them bump stock for the moment, are less smooth. And you can garner a lot of information from this, but the major one here is that they all tend to group around one value, and beyond that value, the probability of these other values occurring is small or smaller. So that would be kind of like saying I step on my disc brakes and they're worn and it goes thump, 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 because the calipers are worn down to that little thing that is the warning that you need to replace them. But the thump, 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 thump is, you know, if you're going fast, it's going to go thump, 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 thump. If you're going slow, it's going to go thump, 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 thump. And as you come to a stop, it'll go thump, 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 thump. And that's what this is really saying. How frequent that thump occurs decreases in if it work hard with the velocity. But this up here would be saying that you mostly press on your brakes at a certain speed. So, for example, this low end might be 30 miles per hour, and that would be the most probable. And that drops a fraction. This is a log scale because it is measured in decibels. So, log scale, the ear hears things on a logarithmic scale. So the logarithmic scale is the most natural to use when you're dealing with sounds, which the time between bullets is a sound. Okay, now this is all three plotted on one graph, and that's the only way this kind of makes sense. Because individually, you look at that line, you go, yeah, big deal. Unless I put some real absolute numbers to it, it makes little sense. But it's very useful for comparing. Now this is one of my favorite ones. This is all three of those things with the same type of graph. It's called an event angle spectrum. And what it does is it takes the time, it takes the muzzle blast time and presumes that each time is a sinusoidal event. And then the question it asks is, for the next event, how close is it to the same time? So, for example, if the first delta was 0.1 seconds, and then the next one was 0.11, then that basically says that peak to peak, that whole thing is being extended by a certain number of degrees or radians, as you might say, degrees or radians. So the peak, if it was real smooth, should occur at 0.1, but since it occurred at 0.11 and the previous one occurred at 0.1, then that is a slight variation in the, and we express it in terms of angles. So you can look at it as kind of like a self-similarity from peak to peak. And it gives us another handle into the finer structure of these things. So, for example, for the machine gun, which is the blue one, it had a couple of huge differences near this the early frequencies, and then it stayed, you know, they were basically the same. So once it got going, the time from shot to shot was almost identical. Had a little bit of trouble near, let's see, is that really, yeah, I think that's the start. I'd have to look at it. I should have put the absolute numbers on here and then I'd know. But I think on the left is the lower shot times, and on the right is the higher. Okay? And what's interesting is that all of them have that same phenomena. So whether it's a machine gun or a volley, they seem to all have a big variation in timing, either near their start or not near the start, but near this frequency, whatever it is. That should be the most common frequency. And then you'll see, then we're going to have to look at these individually, because both volley 10 and volley 7 do some interesting things out there. And down here they kind of follow the same as the machine gun. They stay pretty much, you know, controlled. So that says that all of these, that the volleys have three modes of operation. One with a startup, I shouldn't say startup, around this frequency, smooth for the most part, but then as it gets out to these other frequencies, there's some finer structure, and one of them is more interesting than the other. Let's see if we can find those down here. Be looking for power spectrum. magnitude spectrum. We want angle spectrum. Okay, that's for the machine gun. And this one's interesting. Okay, this is for volley 10. What this basically says is, if we look at it from here to here, you notice they're very similar, but they're expanding in amplitude. And so what this is saying is that there are times between rounds in which one round to the next they are changing, and then it changes back down to what it looked like when it started, and then it repeats the whole thing all over again. So this is some fine structure buried in there about the timing between rounds that we might be able to exploit. If we look at number 7, you know, this part, this consistent part here is kind of similar to that. These parts over there are kind of similar, but these two, they're completely different processes. Or this one doesn't have enough. Let's see. Let's look at data. Yeah, how many data points there? 1, 2, 3, 4, and then see, this one varies so much from one point to the next that we'd have to say something is wrong. Well, I don't know what it means yet. I'll have to look into it. But this one to me is more interesting because there's a pattern there, and it has this growth which looks to be exponential. Okay, so at some point along here, the magnitude of this pattern is growing. And in normal signal analysis, there were some very interesting experiments done way back in the early days of signal processing, done by, I think it was AT&T, where when you started looking at the noise on a line, because after all, if the noise dominates the signal, you don't have good communications. So engineers took a look at the noise level compared to the signal, and the patterns of that noise, and they found that this noise goes along behaving fairly normally, as in a random normal distribution, and then at some point, based upon the level of the signals and the level of the noise, it turns into a pattern that basically bifurcates and then repeats that pattern, and it grows in this nice shape. And it ends up ending into a chaotic pattern with chaos embedded into it. And they exploited that to improve the performance of communications. And then they went on to find out that almost all processes, not only signals, but the heart, for example, followed the exact same pattern. So the heart could be operating along here normally, and then all of a sudden it could start going into a VFib. Okay, and it could follow any one of a dozen routes, but they all ended up in this VFib. And then if you applied electric current, you could shock it back into this normal sinus rhythm. So this, to me, looks almost identical to one of those types of processes. Which, if that's true, then for this volley on 10, then there could be some natural process with tendencies to become chaotic, but that can be forced back into normal operation with the appropriate applied external stimuli. Okay, so that's something worthy of study right there. Whereas this over here is just kind of like, yeah, okay, that's the normal variance in the signal. And for this one, there is no normal variance, so that's some type of machine that has the noise factor well under control. Which it looks like all the 240 series are that way, unless I just happen to catch 50 different volleys from 50 guns that were all well maintained. Could be. Okay, so that's the event angles. We covered the event angle, magnitude spectrum, and let's just go down to the bottom of the list and work the way up. And that's some code. This is basically a 2D equivalent of the histogram, and from it the bright spots on here are the places where the frequency is highest and the probability of operating in that frequency is highest. So this is event 7, which we know to be a fairly regular thing, and we see that there's the brightest one is all dominant right there, and then the other most probable mode of operating is down here, but it's kind of low, so I would expect it to be mostly here. And then we have some of these outliers in these darker colors up here, which we know are probably related to those startup ones. So overall, this has a narrow plane here with mostly dark areas. So this is a fairly well controlled thing. If you want to look at it in terms of the time scale, this is the start, and then this is what the frequencies are across time. Now if we look at volley 10, we see that it's not well controlled, that it's all over the place. In fact, the startup of it is a little out of control because of the range and values, and then gets a little bit back in line, and then as we go further, this keeps growing and growing and growing. Although this one was well controlled. There's something right there which is fairly well controlled, but other than that, it just keeps growing and growing. So it's out of control in many regards. Now the machine gun has this nice neat line that kind of follows the timing, and the scale is huge, and if we scrunch the scale down and applied it onto one of these, it would just look like one of these straight across. So really these are kind of a mixture between the plot of delta t's versus time and the histogram all rolled into one. And I call them the poor man's spectrogram. So, alright, so anyway, I've covered those. I don't use them very often because I just roll over into Sonic Visualizer and get the real thing. This is another technique. This is a technique called delaying, where we take the same exact signal and we measure against itself by delaying the signal X amount and seeing if the signal coincides with itself. And if it does, then it's very similar to itself. Okay, now this is another way of finding out whether a signal has a narrow operating frequency that it prefers. In this case, volley 7, we see that these things all congregate down here, the most dense part between 0.08 and 0.1, which fits our understanding of that volley pretty well. And let's see, volley 10 on the other hand, you can see that there's one dominant frequency right there, and then other than this one right there, it's spread out all over the place. And this one doesn't count because again the scale is off. If we crunched it down to the same scale as these, then it would be much narrower than this. So again, I probably should go back and modify these graphs so they all have the same scale, so that when I'm looking at them, I can compare them. It's a work in progress. Okay, this one was we covered that one, we covered that one, we covered that one. That one, histograms individually and collectively, delta t versus shot count for 7, we covered that. We covered those. Okay. Yes, covered those. Covered those. Now there's one of those delays all plotted together, which unless I, make each one a different colors is essentially useless. We covered the event angle spectrum collectively, magnitude spectrum, histograms, delta t, stem, RPM. In this case you have two RPM plots that are identical except for the scale down here. And this one up here is real time, absolute time, 10 p.m. and 22 minutes and 10 seconds. I think I read that right, didn't I? Yeah. So in this case, this volley was at, no, I was wrong. It's 10:07, 10:08, 10:09, 10:10. Yeah. So there's no second mark on there. That's per minute. these divides are a minute. Anyway, in this case, it's real time. This time it's video relative time. Okay. Now, that covers those basic graphs. You can see the types of questions. You can see what types of answers we might get. You can see what types of hypotheses we might form. We see what kind of distinctions we can make between them. This doesn't show all the data. It doesn't show all the reference points. But when you start putting it all together, you start to develop this better understanding of what's happening. And you build a base of confidence. And hopefully you're driving to a convergence point. And then once all that's done, you have a well-founded, well-researched, well-thought-out, data-driven basis to leverage into something bigger. So bottom line is here, what are the types of questions that you want to ask? And what are the types of answers you're looking for the data to supply you with? And put those in the comments, and we'll go from there. Because I've got 100 other different types of graphs that I use. Some of them don't make too much sense. Some of them provide wonderful insights into some of the volleys. You never know. And then, of course, on the other side of the coin is that I can apply any form of signal processing, filtering or analysis, separations. I can take a signal and separate it into vocal and non-vocal. I can take a signal and separate it into foreground, background. I can take a signal and separate it into the harmonic and the percussive, and dozens of other operations. High pass, low pass, band pass, Buttersworth, and the list goes on. If you have something that you think is valuable, that other people can use, that it's worth me investing my time in, put it in the comments. Let's talk about it. Let's see what we can gain from it. Let's see what leverage we can bring to the whole analysis process. And the only thing we're lacking is a way of effectively sharing all this. I have a GitHub account which I'll put things on which you can download from, but it seems as though a lot of people aren't really accustomed to that mode of operating and need a different thing. The biggest thing that I've enjoyed about the Vegas researching is that somebody took the time to put together the Vegas map project, that listed all the dots on a map and what they were, where the video was, and then somebody, and I applaud these people for doing it, took the time to listen to everyone and show me, both in video relative time and absolute time, where the volleys started. That's an invaluable tool. I use it every day, 10, 20, 30 times a day. And without that, I'd have had to do that myself. And it would have been far worse in shape than it is. If I had done it, it would be in far worse shape. And it's something I didn't have to do that I can leverage. And this type of work that I'm doing now, by measuring all these things, is something that somebody else doesn't have to do, which, if they have the skills necessary to look at the data, could provide a major breakthrough for them. Anyway, that's pretty much it on this one. We'll grab you in the next one. And this is Vegas October 1 Sound signing off.